electric modes or TE modes. So in TE modes, Ez is equal to 0, Hz is not equal to 0. So here I am giving the equation for Hz. Hz is equal to H0 into cos m pi by a x cos n pi by b y e power minus gamma z. Here, if you observe, if you differentiate this equation with respect to TM modes, in TM modes, for Ez, the equation is in terms of sine terms, whereas here, Hz is in terms of cosine terms. This is the first point. And the next point is Fc, cutoff frequency, lambda c, cutoff wavelength, beta, phase constant, Vp, phase velocity, and lambda g, guide wavelength for TE modes are same as TM modes. So the formulas what we use for TM modes, the same formulas also valid here for TE modes for Fc, beta, phase velocity and lambda g. Another third important point is for TE modes, Mn may be 0, 1 or 1, 0. 0, 1 or 1, 0, but not 0, 0. But not 0, 0. That is, both M and N cannot be 0 at the same time. If both are 0 at the same time, all field components vanishes. So any one value is 0. But if you compare this statement with respect to TM mode propagation, the difference is in TM mode propagation, M is not equal to 0 and N is not equal to, that is either M or N not equal to 0. So the lowest possible mode there is TM11, but here 1 may be 0, that either M is 0 or N may be 0. It is valid, but both are not be zeros at same time. So here 0, 1 and 1, 0 combinations are possible, whereas these combinations are not possible in TM modes. So what is the lowest possible mode? So this implies that the lowest mode can be the lowest mode can be, so what is the lowest mode? Either TE01 or TE10 depends upon values of A and B. Depends upon values of A and B. That is, TE01 means what? Cutoff frequency is equal to, we know that C by 2 into square root of M by A whole square plus N by B whole square. So for TE01, so M is equal to 0. So what is Fc? C by 2 into N by B. Similarly, for TE10, what is Fc? Fc is equal to C by 2 into M by B or M by A. Since it is TE10, C by 2A, whereas for TE01, C by 2 NB, N is equal to 1, Fc is equal to C by 2B. So here, depending upon A and B values, so the lowest possible mode exists. The condition is, in standard waveguides, that is practical waveguides, we have A greater than B. A greater than B always. A greater than B always. Then what this means implies A greater than means Fc is equal to C by 2A for TE10. Fc is equal to C by 2B for TE01. Since A is greater than 1, TE10 is the lowest mode. 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 Because Fc is equal to C by 2A for TE10. This mode is also called as dominant mode. Dominant mode of the waveguide. This mode is also called as dominant mode of the waveguide. Here the definition for dominant mode is it is a mode which has lowest cutoff frequency or longest cutoff wavelength. So dominant mode is a mode which has lowest cutoff frequency or longest cutoff wavelength. Here one important thing is TM11. TM11 is the lowest mode possible for TM wave propagation, but it is not a dominant mode. Dominant mode means lowest cutoff frequency. Of course, for TM11 in TM propagation it has lowest cutoff frequency, but it is not a dominant mode, because if you compare with TE10 cutoff frequency Fc, TE10 Fc and TM11 Fc, TE10 has lowest cutoff frequency. TE10 has lowest cutoff frequency. That's why TE10 is the dominant mode for the entire waveguide. Either it is a TE propagation or TM propagation, irrespective of the propagation, TE10 is the dominant mode. TM11 is not the dominant mode. It is the lowest possible mode for TM wave propagation. That's all. If you compare the cutoff frequencies for these two, TE10 and TM11, TE10 has lowest cutoff frequency. Therefore, TE10 is the dominant mode of the waveguide. And it is also the lowest possible mode in TE propagation. Another important definition of, or point, another important point is Another important point is degenerate modes. Degenerated modes. The definition for this is, if two or more modes, if two or more modes have same cutoff frequency, then the modes are called as degenerated modes. Degenerated modes. That is, the modes with the same cutoff frequency. The modes with same cutoff frequency are called degenerated modes. And next point is intrinsic impedance. Intrinsic impedance, eta TE. The intrinsic impedance for TE mode is given by eta dash by square root of 1 minus fc by f whole square. It is eta TE is greater than eta dash. Because if you multiply eta TE and eta TM, so we will get only eta dash square. Therefore, eta dash or free space impedance is given by eta TE into eta TM. That is, if you represent graphically, this is eta dash. So eta TE, this is suppose cutoff frequency. Eta T is always greater than eta dash, and this is eta TM. This is eta dash 120 pi reference. Now we will discuss some problems on waveguides. The first problem is a rectangular waveguide filled with a dielectric material of relative permittivity four has the dimensions 3.0 centimeters cross 1.2 centimeters. The cutoff frequency for the dominant mode is option A 2.5 gigahertz, option B 5.0 gigahertz, option C 10.0 gigahertz, option D 12.5 gigahertz. So this kind of problems are very important. Now we will discuss what is the solution, how to solve this type of problems. So the solution to this problem is, here they are asking what is the cutoff frequency for the dominant mode. So we know that dominant mode is Dominant mode is TE10. TE10 is the dominant mode. So what is the cutoff frequency? Fc is equal to C by 2 square root of m by a whole square plus n by b whole square. Here m is equal to 1, n is equal to 0. So directly we can say C by 2 into m by a. M is equal to 1, that is equal to C by 2a. C by 2a. So this is the cutoff frequency. Here what are the dimensions? Dimensions are given 3.0 centimeters cross 1.2 centimeters. We know that for a standard waveguide, A greater than B, standard waveguide. So this is A value, this is B value. So A value is here is 3. Therefore cutoff frequency is equal to C by 2 into 3. Here centimeters. So directly I am taking in centimeters. 2 into 3. So 6. Total centimeters. 6 in C by 6. Here it is very important. Here in the given statement it is mentioned that the waveguide is filled with a relative permittivity of 4. Where C is here. C is equal to 1 by square root of mu naught epsilon naught. Mu naught epsilon naught, that is free space velocity. But here it is given a material. Generally waveguide is filled with air. But here in this problem it is given that the waveguide is filled with a dielectric material of relative permittivity 4. So we have to consider the value is not 3 into 10 power 8 meter second. The value is C is equal to, now we have to consider 1 by square root of mu naught epsilon naught and epsilon r also into account. So it will be 3 into 10 power 8 meters, or here I am considering centimeters. So directly 3 into 10 power 10 centimeters by square root of epsilon r. So square root of epsilon r means here what is epsilon r? 4. So square root of 4. Square root of 4. Therefore cutoff frequency is equal to 3 into 10 power 10 by 6 into 2. 6 into 2. So that is 3 by 12, 1 by 4. So 1 by 4. 1 by 4 into 10 power 10. So here it is given in everything in terms of gigahertz. So I am writing it as 10 by 4 gigahertz. 10 by 4 gigahertz. So 10 by 4 means how much? 2.5 gigahertz. 2.5 gigahertz. So the cutoff frequency is 2.5 gigahertz. So option A is correct. A is correct. So in this problem, so here we have to know three concepts. One is what is the dominant mode. So here indirectly they are mentioning TE10 mode, because TE10 mode is the dominant mode. And one more thing, here the dimensions are given 3 by 1.2. So we know that in standard waveguide A is always greater than B. So we are considering A as 3 here. And one more thing, very important is, here the dielectric is filled with a relative permittivity of 4, epsilon r value. Generally we are considering everything in free space, air. That is C is equal to 3 into 10 power 10 centimeters per second. Since it is filled with dielectric material, we have to take epsilon r value also into account. That's why we are dividing with the square root of epsilon r C value. So if you do like this, you will get exact answer. If you miss any one thing, so the answer will be wrong. So keep in mind this point, which is very important for solving problems. Permittivity. Next problem is the phase velocity for TE10 mode in air filled rectangular waveguide is the bracket. C is the velocity of plane wave in free space. This is the question. The options are option A less than C, option B equal to C, option C greater than C, option D none of the above. So this is a very good question. Already we discussed the concept. We know that phase velocity is equal to c by square root of 1 minus fc by f whole square. Phase velocity is greater than c for a given value of f. So here they are asking the phase velocity for TE10 mode in air-filled rectangular waveguide is. So generally, obviously, it is greater than c. Greater than c. Phase velocity is greater than c. But the phase velocity is greater than speed of light in vacuum. So actually, this is violating Einstein's relative theory. Relative theory. What is Einstein's relative theory? The messages cannot travel faster than speed of light. But here we are getting Vp greater than c. The phase velocity in a waveguide is greater than speed of light. So which is practically not possible. So generally what is the thing is here in a waveguide the energy or the wave does not travel with the phase velocity. It is travel with the group velocity. The wave will travel with the group velocity which is less than speed of light. Which is less than speed of light. So this is very good concept of waveguide. So the option for this given question is clearly C. Clearly C. Next problem. Problem number 3. A rectangular waveguide having TE10 mode as dominant mode is having a cutoff frequency of 18 gigahertz for TE30 mode. Is having a cutoff frequency of 18 gigahertz for TE30 mode. The inner broad wall dimension of the rectangular waveguide is option A 5 by 3 centimeters, option B 5 centimeters, option C 5 by 2 centimeters, option D 10 centimeters. 10 centimeters. So the solution to this problem is here the dominant mode of the waveguide is TE10 they are saying, and it is having a cutoff frequency of 18 gigahertz for TE30 mode. So I know that cutoff frequency is equal to C by 2 into square root of m by a whole square plus n by b whole square. So cutoff frequency is equal to 18 into 10 power 9, 18 gigahertz for TE30. So C by 2 into only m by a, that is 3 by a. They are asking what is the inner broad wall dimension. So inner broad wall dimensions mean nothing but they are asking for A. Broad wall dimension is A. So we have to calculate what is A. What is A? So here if you simplify this, where C is equal to 3 into, so 18 into 10 power 9 is equal to 3 into 10 power 10, because here everything options, if you observe the options, all the options are in centimeters. That's why I am also using here 3 into 10 power 10 by 2 into 3A. Therefore, A is equal to 9 into 10 power 10 by 36 into 10 power 9, that is equal to 1 by 4 into 10, that is equal to 5 by 2 centimeters. 5 by 2 centimeters. Therefore, A is equal to 5 by 2 centimeters. A is equal to 5 by 2 centimeters. So, option C is correct. Option C is correct. Then, why here they mentioned TE10 is here? Just they are mentioning TE10 is the dominant mode. TE10 is the dominant mode of the waveguide. Actually here this TE10 is not useful for our calculation. Just it is given a statement, the waveguide has TE10 mode as dominant mode, having a cutoff frequency 18 GHz for another mode TE30. So this statement TE10 is not useful for our calculation here. So don't confuse with the TE10. The next problem is problem number 4. If in a rectangular waveguide for both A is equal to 2B, the cutoff frequency for TE02 mode is 12 GHz. The cutoff frequency for TM11 mode is option A 3 GHz, option B 3 into root 5 GHz, option C 12 GHz, option D 6 root 5 GHz. So this is another kind of problem. The solution to this problem is, here it is given A is equal to 2B, rectangular waveguide for which A is equal to 2B. The cutoff frequency for TE02 mode is 12 GHz. So first of all I am calculating TE02 mode. So for TE02 mode, what is cutoff frequency? FC is equal to, I know, C by 2 into M by A whole square plus N by B whole square. So if you don't remember this formula, it is impossible to solve the problem. So keep in this cutoff frequency formula or all formulas what we discussed so far. Now here I want FC 02. So M is equal to 0, N is equal to 2. So that is equal to C by 2 into N by B. N by B. So that is equal to C by 2 into N is equal to 2 by B. So 2 cancels. Only the thing is that is equal to C by B. But the cutoff frequency is given as 12 GHz. Therefore, C by B is equal to 12 GHz. 12 GHz, that is 12 into 10 power 9. Now, C is equal to 3 into 10 power 8 meters per second. Therefore, B is equal to 3 into 10 power 8 by 12 into 10 power 9. 12 into 10 power 9. That is equal to 1 by 4, 1 by 40, 1 by 40 meters, or 100 by 40 centimeters, 100 by 40 centimeters. So 100 by 40, that is 10 by 4, 5 by 2 centimeters, 5 by 2 centimeters B value. Then A is equal to how much? A is equal to given 2B. A is equal to 2B, that is equal to 2 into 5 by 2. So that is equal to 5 centimeters. A is equal to 5 centimeters. Then what is the cutoff frequency for TM11? So that is equal to cutoff frequency is equal to C by 2 into square root of M is equal to 1, M by A. So 1 by A whole square plus 1 by B whole square. So that is equal to C by 2 into square root of 1 by A. So that is equal to 1 by A means A is equal to 5, 1 by 5 whole square plus 1 by B, that is 2 by 5 whole square. So that is equal to C by 2 root 5, that is equal to 3 into 10 power 10 by 2 root 5. So if you simplify further, Fc is equal to, I am writing 3 into 10 by 2 square root of 5 gigahertz, because 10 power 9 is equal to 1 gigahertz, that is equal to 3 into 5 by root 5, because 2 5s. So this is nothing but 3 root 5 gigahertz, 3 root 5 gigahertz. So what is the answer? Answer is option B is correct. Option B is correct. So the only thing is here, when you are calculating, you must calculate accurately. So accuracy is important in waveguide problems. So you will get very simple problems in waveguide. So just use the formula and calculate accurately. So this is another kind of problem.